Hi guys, welcome back to my channel Gamma Die Gamma. So in this video, I thought let's take a break from the integrals, let's take a break from the tedious gamma functions. Let's focus on a topic that I already made a video on, I think a few years ago. I think it was during the pandemic. It was on the Wallis product. I had outlined 4 ways to prove the Wallis product, and I have found another one online, and I thought I should share it with you guys because this actually closely follows the proof of the Basel problem in the very previous video. So I urge you to check that out if you haven't already. That proof is the most elegant proof I have come across till now. And then this proof that I'm going to present today is also in those category of elegant proofs. So let's get started without any other delays. Okay, so when I said we're going to follow the proof in the last video, I meant this complex analysis part. So first of all, we begin with the Moivre's theorem. So that says e to the I mz equals e to the iz, whole thing to the m power. Now you might say this is a direct consequence of the associativity of multiplication of multiplication between functions, but it has very nice consequences in the sense if you write the exponential in terms of its cosine and sine equivalent part using Euler's formula, you end up with cosine of mz plus I times sine of mz equals cosine z plus I sine z, the whole thing to the mth power. Now cosine mz plus I sine mz, which is the left hand side, equals the right hand side, and we can expand the right hand side using the binomial theorem. So in the binomial theorem, we have a sum going from k equals 0 to m. We have m choose k, which is a combinatorial coefficient for combination. Cosine to the m minus k power of z times I sine z, whole thing to the kth power. So as you see, when we are summing it up, we start with 0. When k is 0, we have cosine m, and then sine has power 0. And then as we increase, we're going to have coefficients that are not equal to just plain 1. And we're going to increase until we reach the very end m, where the cosine term vanishes and the I sine z term has full power, has power m. So I've written down a few terms for you. The main thing with this is we're gonna notice which terms have an I, which terms don't have an I, because the ones that do have an I just contribute to the imaginary component, while the terms that are without the I contribute to the real component. So the real component has the even values of k. So that means we have m choose 0 cosine z minus m choose 2 cosine of m minus 2 of z sine squared z. Why do we get a minus? It's because we square the I in the second m choose k term. And then plus or minus so on, because we're going to alternate if you look at the pattern, because I of 0 is 1, I squared is minus 1, I to the 4th is going to be the next term, which is 1, and then I to the 6th is going to be minus 1. So you see there's a pattern of alternating plus and minus. That's why I have the plus and minus dot dot dot. The imaginary terms are going to be the odd values of k. So m choose 1 cosine to the m minus 1 sine z minus, and now why do we get the minus? Because it's I cube is minus I, and we've already factored an I outside, so we have a minus m choose 3 cosine of m minus 3 of z sine cube of z plus or minus so on, because again the signs will alternate just like the real component. Okay, fair enough. We're going to move forward now. So when we move to the imaginary part now, we just look at the sign here because that's the term which contributes to the imaginary part. The cosine does not. And we also then care about the imaginary part of the right hand side, which is just the odd values of k. in the sum here. So we can equate both of them. Sine of mz equals m choose 1 cosine m minus 1z sine z minus m choose 3 cosine m minus 3z sine cube z plus or minus so on. We can make a choice for m. We can choose m to be odd in the sense m is equal to 2n plus 1, where n is some arbitrary integer. And we will then have sine of 2n plus 1 z then equal to k equals sum from k equals 0 to n. Instead of writing it in a free form like this, we can write it in a more compact form now that we know that m is odd, because now we know that the sum is going to terminate always at 2n plus 1, and we can sum from k equals 0 to n. So we have 2n plus 1, choose 2n plus 1, minus 1 to the k because we're alternating the signs, cosine to the 2n minus 2k, because this was the difference between 2n plus 1 and 2k plus 1, which ends up being 2n minus 2k. And we have sine of the bottom part, so sine of 2k plus 1 of z. Let's call that equation 1. This entire thing is equation 1. All I've done is I've written m as 2n plus 1. I've assumed that it's odd, and then I have written this free form in white into a more compact form using the sigma notation for the sum. Now, if we divide by sine z and times cosine to the 2n of z, we end up with sine to the 2n plus 1 of z divided by sine z cosine to the 2n of z equals k equals sum from k equals 0 to n, 2n plus 1, choose 2k plus 1, minus 1 to the k, and we actually end up with a tangent to the 2k of z. Let's call that equation 2. Let's divide equation 1 by sine to the 2n plus 1 of z. So when we do that, we have sine of 2n plus 1 of z divided by sine to the 2n plus 1 of z equals sum from k equals 0 to n, and 2n plus 1, choose 2k plus 1, minus 1 to the k, cotangent of 2 times n minus k of z. So then we can define a polynomial like we did in the last video. We can set t equals cotangent squared of z. When we do that, this entire equation that we had before can just be written in as sum from k equals 0 to n, 2n plus 1, choose 2k plus 1, minus 1 to the k, t to the n minus k, and we can call that p of t. It's a polynomial in t. The degree of the polynomial, or the highest power in the polynomial, is actually n. So by the fundamental theorem of algebra, there's going to be n roots, and you'll see if when we try to find the roots of p of t, we have to set sine of 2n plus 1 of z equal to 0. So that means 2n plus 1 times z equals k pi, where k is some integer. So z has to be k pi over 2n plus 1. And now I'm quoting the fundamental theorem of algebra. The polynomial has n roots because it has degree n. So therefore k can only take n values, because k is the only thing that's actually changing. 2n plus 1 is fixed, in our case pi is fixed. So 1 is less than or equal to k, less than or equal to n, where k is an integer. Now you can see that, this is the only unique set of values for z. In the last video, where I argue that if we take any other values where if k is greater than n, then we actually just end up repeating this set of 1 through n for the cotangent squared function. So please check that out. That's another justification for why k is between 1 and n like this. The more solid justification is just the fundamental theorem of algebra. So the roots are actually tk equals cotangent squared of k pi over 2n plus 1, where k is between 1 and n, both inclusive. Now we know from the remainder theorem that any polynomial can be factored by its roots. So if we have a polynomial q of x that is a naught x to the n plus a1 x to the n minus 1, so on till a sub n, where the degree of the polynomial is clearly n here, the highest power, we can factor out the coefficient of that of that leading term, a naught, and then factor out the remaining x minus x1, x minus x2, so on, x minus xn, where x1, x2, so on till xn are the roots of qx. And by the fundamental theorem of algebra, there's n roots. Okay, so we have the polynomial of p of t. We can expand it using this fact that we know on top here. So when we do that, we have the leading coefficient. The leading coefficient of p of t. Let's go back to p of t. Is when k equals 0, because that's when we'll have t to the n. So when k equals 0, we have 2n plus 1, choose 1. That's the leading coefficient, fair enough. That's the a naught. So we can write that out, and then we can factor the rest of it out as a product from k equals 1 to n of t minus tk. But we can again plug back that t equals cotangent squared of z, and tk equals cotangent squared of k pi over 2n plus 1, where k is between 1 and n, both inclusive. So therefore we end up having 2n plus 1, choose 1 is just 2n plus 1. Product from k equals 1 to n, cotangent squared g minus cotangent squared k pi over 2n plus 1. Now if we multiply both sides by the tangent to the 2n of z, the denominator becomes sine z times cosine to the 2n of z equals 2n plus 1, product k equals 1 to n, 1 minus tangent squared, because we can there's n factors, we can put a tangent squared in each of these factors in the product like this. So that gets rid of the cotangent, that's why we get a 1 minus, then we have a tangent squared times cotangent squared k pi over 2n plus 1. Now combine this with equation 2. What was equation 2? Well, I'm going to write that down for you. Equation 2 was just this. That sine of 2n plus 1 of z equals sine z times cosine to the 2n of z equals sum from k equals 0 to n. 2n plus 1, choose 2k plus 1 minus 1 to the k tan to the 2k of z. So you see the left hand side is the same in this yellow equation and also equation 2, which is the green equation I've written down. So we can set the right hand sides equal to each other by transitivity of equality. So we end up having 2n plus 1, choose 2k plus 1 in the sum from 0 to n, minus 1 to the k tan to the 2k of z equals 2n plus 1, product from k equals 1 to n, 1 minus tan squared g times cotangent squared k pi over 2n plus 1. Just do a small substitution, change z to arctan of z over 2n plus 1. What that does is get rid of the tangent function, just giving us a z over 2n plus 1 to the 2k. And then everything else is practically the same except for the product, which is 1 minus z over 2n plus 1 whole squared times, again, the cotangent squared k pi over 2n plus 1. So all this does is get rid of the tangents on both sides of the equation. Now we can just normalize, we can divide both sides by z over 2n plus 1. When we do that, we have z over 2n plus 1 raised to 2k plus 1, just because we added another factor of that. While on the right hand side, we lose the 2n plus 1, we just get a z. Everything else is the same. Now observe that this thing on the left, it's a sum from 0 to n, 2n plus 1, choose 2k plus 1 minus 1 to the k, z over 2n plus 1 to the 2k plus 1. You see it's actually a sum over all the odd terms, and we also have an alternating sign. Where have we seen this before? We've actually seen this at the start of the video, where we actually group the terms. So you remember we grouped the imaginary terms. The imaginary terms always had an odd k going on, and they also had these alternating plus and minus signs. More precisely, if you look at the compact form here, you notice that if we actually set the cosine to 1 and the sine to whatever we had down there, we actually end up with the imaginary part. Whenever we're summing over the odd terms or the odd k values, we're actually, and with the alternating sign, we're actually dealing with an imaginary part of something like this. So what that means is this quantity here is actually just the imaginary part of 1 plus iz over 2n plus 1 whole thing raised to 2n plus 1. Because see, the top value is 2n plus 1, so the highest, the power you're raising the expression to has to be 2n plus 1. We have 2k plus 1 because we have an imaginary part, and we're, therefore we have odd k values. But also in this there should have been some some term that's raised to the 2n minus 2k power, which is the difference of the first argument and the second argument, as we would have by the binomial theorem, except we don't have that, so that has to be 1. So therefore, if you apply the binomial theorem to this and take the imaginary part we've done, you can also check by that way that it actually equals this. So imaginary part of this expression, and you can use the polar representation to actually convince yourself, is just 1 over 2i times 1 plus iz over 2n plus 1 to the 2n plus 1 minus 1 minus iz over 2n plus 1 raised to 2n plus 1. And all of this equals, according to the blue equation, z times product k equals 1 to n, 1 minus z over 2n plus 1 squared cotangent squared k pi over 2n plus 1. Now we can take the limit as n goes to infinity, and notice that all these guys, the guys on the right hand side of the pink equation, that have these exponential looking things, they actually evaluate to e to the iz and e to the minus iz just by the definition of the exponential function. So we have 1 over 2i e to the iz minus e to the minus iz equals limit n goes to infinity z times product k equals 1 to n, 1 minus z over 2n plus 1 squared cotangent squared k pi over 2n plus 1. So this just becomes the sine by definition. So sine z equals z times, we can actually take the limit. Now, to take the limit inside a product like this, you need some theorems. I'm going to bypass that for now because it actually holds. I just don't want to get into too many details. We have the product from k equals 1 to infinity. We have 1 minus limit n goes to infinity of cosine squared of k pi over 2n plus 1. I'm just splitting the cotangent as cosine squared over sine squared because I can use some nice properties. And then we have z over 2n plus 1 squared, and then the sine from the cotangent in the denominator. We can pull out a few things. So we can pull out the z squared and k squared pi squared in the denominator. So we just end up with a k pi over 2n plus 1 squared in the numerator divided by sine squared of k pi over 2n plus 1 in the limit as n goes to infinity. This actually is just the form sine u over u as u goes to 0, because as n goes to infinity, 1 over 2n plus 1 goes to 0. We can rearrange everything. We can take a new variable, change the variable, and see that this is actually sine of u over u, just flipped. It's 1 over sine of u over sine of u, the whole thing squared, which actually evaluates to 1. It's a famous limit. So sine z equals z times product from k equals 1 to infinity of 1 minus z squared over k squared pi squared. And this is the famous Wallis product formula. It's a product representation of the sine, or more precisely the sinc function, because we have sine z over z. And this is basically what we use to prove Euler's reflection formula, because once we have a product representation of a gamma function, just multiply gamma of z and gamma of 1 minus z, and you end up with a product that looks like this Wallis product. And it's a very nice product. It helps you prove a lot of things, like the derivative of the Riemann zeta at 0 as an example. But that's it for this video. I hope you liked the proof. It was a little long and it might have felt unmotivated at times, but it actually follows closely from the idea we had before. The main points of elegance were basically how the exponential just pops out from using the imaginary part of the binomial expansion that we've been dealing with throughout this video and also the previous video. Let me know if you have any questions. I notice I may have, been a little abrupt with some things, so just drop a comment. Okay, peace out.